Okay, now we are going to learn about energy stored in a capacitor. Energy stored is also known as work done. When a capacitor's plate store charge, they are also actually storing energy. So when the switch is closed, the charges will begin to accumulate on the capacitor's plate. So a small amount of work dW is done in bringing a small amount of charge dQ from the battery to the capacitor. So basically, work is done to bring charge from battery to capacitor. And this is given by dW is equal to V dQ, where V is equal to Q over C. And you can substitute V into the equation to get dW is equal to Q over C dQ. To find the total work required to increase the accumulated charge from 0 to Q, which is the maximum charge, is then given by the integral of dW from 0 to W is equal to the integral of Q over C dQ from 0 to Q. Once you have done the integration, you will get W is equal to 1 over 2 Q squared over C. And this is also known as the energy stored, which is what we label as U. And we also know that Q is equal to CV. Hence, we can actually write this formula in another form where U is equal to half CV squared, or you can also write it as U is equal to half QV. Let's look at example 5. An electronic flash unit for a camera contains a capacitor of capacitance 850 microfarad. When the unit is fully charged and ready for operation, the potential difference across the plates is 330 volts. So A, what is the magnitude of the charge on each plate of the fully charged capacitor? And B is asking us to find the energy stored in the charged out flash unit. First, go through the question and identify which information is given to you. So we actually have the capacitance, which is 850 microfarad. And then we also have the potential difference, which is 330 volt. So question A asks us to find the magnitude of the charge, which is actually Q. To find Q, you can use the formula Q is equal to CV. And then you have the values of C and V, so just substitute in those values. So 850 times 10 to the power of negative 6 because 850 micro. And then times with 330 and you will get Q is equal to 0.285 coulomb. And then for energy stored is U. So just use the formula of U, which is equal to half QV, or another formula that you can use is half Q squared over C. And then another formula that you can also use is half CV squared. So let's say I use half QV, then just substitute in values of Q and V to get U, which is 47.025 joule. Now we are going to look at the charging and discharging of capacitors. So capacitors can do two processes, which are charging and discharging. But before that, we are going to learn about time constant tau. So time constant tau is the product of RC. So you can write the formula as tau is equal to RC, in which R is the resistance of the resistor. The unit is in ohms. And then C is the capacitance of the capacitor. Time constant is a scalar quantity and the unit is in second. It is also a measure of how quickly a capacitor charge or discharge. So to define time constant for a charging process, we can look at three graphs. So we have V against T, Q against T, and I against T graph. So let's look at V against T and Q against T. So these two graphs have the same exponential trend. And then if you see at V against T graph, you can see that the time taken for the voltage to increase to 63% of its maximum voltage is equal to the time constant tau. So that is why we get the definition for the time constant tau, in which it is the time required for the capacitor to reach 63% of its maximum charge or maximum voltage. Meanwhile, if we look at the I against T graph, we can see that the time taken for the current to drop to 37% of its initial value is equal to the time constant tau. We can also define the time constant based on the graph of Q against T, V against T, and also I against T for discharging process. As you can see from the graphs, the time taken for the charge and also the voltage to drop to 37% of its initial value is equal to the time constant, and the same applies for current as well. Now we are going to sketch and explain the characteristics of Q against T and IT graph for charging and discharging process. So as mentioned before, capacitor can do two processes, which are charging and discharging. So we are going to look at charging a capacitor through a resistor first, which is a charging process. So the figure shows a simple circuit for charging a capacitor. A capacitor can be charged by connecting it in series with a battery and also a resistor. When you charge a capacitor, the number of charges inside it will increase. When the switch is closed, the charges will flow from the negative terminal of the battery, and then it will accumulate on the plates of the capacitor. So we can see from these two graphs, for example from the Q against T graph, the number of charges in the capacitor will increase exponentially until it is fully charged and it reaches Q0. So Q0 is the maximum number of charges. And then for voltage against time, VT graph, we know that as the number of charges increases, then the voltage will also increases exponentially at the same rate. And this can be written in the form of an equation. So for Q against T, we can write this formula in which Q is equal to Q0 bracket 1 minus exponential negative T over RC, where Q0 is the maximum number of charges and Q is the instantaneous charge at particular time T. And for V against T, we have the formula V is equal to V0 bracket 1 minus exponential negative T over RC, in which V0 is the maximum voltage and V is instantaneous voltage at a particular time T. For I against T, as the capacitor store more and more charges, the rate of current will decrease and then capacitor will be fully charged. So once capacitor is fully charged, there will be no more charge flowing. Current in the circuit will then fall to 0. So current in resistor for a charging process can also be written in the form of I is equal to I0 exponential T negative T over RC, in which I0 is the maximum current and then I is the instantaneous current at a particular time T. And we can also find I0 using the formula I0 is equal to V0 over R. Okay, so now let's look at discharging a capacitor through a resistor, which is a discharging process. The figure shows a simple circuit for discharging a charged capacitor. So as you can see, a capacitor can be discharged by connecting it in series with a resistor and without a battery. Discharging a capacitor is a process when charges flow out of the capacitor, and this happens when the switch is closed, which allows the charge to flow out. And then from these graphs, we can see that the number of charges in the capacitor will decrease exponentially until fully discharged when the charges are reduced to 0. And as the number of charges decreases, the voltage across the capacitor will also decrease at the same rate. So we can write it in this form of equation. Q is equal to Q0 exponential negative T over RC, in which Q naught is the maximum charge and Q is the instantaneous charge at particular time t. We have V is equal to V naught exponential negative t over RC, in which V naught is the maximum voltage and V is the instantaneous voltage at a particular time t. And from I against T graph, we can get the formula for current in resistor, which is I is equal to negative I naught exponential negative T over RC. The negative sign indicates that as the capacitor discharges, the current direction is opposite to its direction when the capacitor was being charged. And for calculation, you can ignore the negative sign. Okay, for example 6, we have an RC circuit as shown in the figure. So initially the switch S is at position A. When switch S is at position A, the capacitor experiences a charging process, which happens until the capacitor is fully charged and it reaches the maximum charge Q naught. So we can start out by finding what is Q naught by using the formula of Q naught is equal to CV naught, in which C is the capacitance, which is given in the question, 3 microfarad. So 3 times 10 to the power of negative 6 times by the battery voltage V naught, which is 12 volt. And then we will get the maximum charge, 36 times 10 to the power of negative 6 coulomb. And now we can proceed with the first question, which is asking us to find R. So R is resistance, and you can find it using the formula for current in a resistor for a charging process, which is I is equal to I naught exponential negative T over RC. So we have to substitute I naught, and also T and C to get R. So we don't have the value of current, but the question mentions that the current is observed to decrease to 0.45 of its initial value. So you can write it as I is equal to 0.45 I naught. And then you can substitute this into the original equation. You will get 0.45 I naught is equal to I naught exponential negative T over RC. You can cancel out I naught from both sides, and then what you have to do is substitute in time and also capacitance. So they are both given in the question. Time is 60 microsecond and the capacitance is 3 microfarad. Substituting those values will get you the equation in the form of this. And then now we have exponential. So to get rid of the exponential, you have to use ln 0.45 is equal to ln exponential of that, and then you can cancel out the ln to get this, and then you just have to use your calculator to solve for R. The final value of R will be 25 ohms. Then the second question asks you to find the time constant tau. So you can use the formula tau is equal to RC, and you have the value of resistance and capacitance. So just substitute in the values of R and C, which is 25 times 3 times 10 to the power of negative 6. And you will get time constant is equal to 7.5 times 10 to the power of negative 5 seconds. And then for C, you want to find Q, which is the charge on the capacitor at time equal to 0. So at time is equal to 0 second, the switch will be thrown from position A to B. So once the switch is at position B, the capacitor will experience a discharging process because the capacitor is not connected to the battery anymore. To solve this, we can use the formula of Q for discharging process, which is Q is equal to Q naught exponential negative T over RC. So we have Q naught, which is 36 times 10 to the power of negative 6, and then we have the time, which is 0, and R and C, So 0 divided by R and C, we get 0 as well. And this will be equivalent to 1. So your final answer will be 36 times 10 to the power of negative 6 coulomb. And then for question D, we want to find Q at 100 microsecond. We assume this process is still a discharging process. So we can still use the same formula as the previous question, which is Q is equal to Q naught exponential negative T over RC. Q naught is 36 times 10 to the power of negative 6. And then the time is 100 times 10 to the power of negative 6 divided by the resistance, which is 25, and the capacitance, which is 3 microfarad. Then you will get the charge is equal 9.49 times 10 to the power of negative 6 coulomb.